Bismillahirrahmanirrahim. This is the third lecture of chapter 3. So we will be completing chapter 3 in this lecture. So today's in this lecture we will solve example 3-1 from your book. Let's go to the book. This is your engineering fundamental of the internal combustion engine, your reference book by Willard. Now, example 3-1. First, I will read the example and then I will explain. Statement is a four-cylinder 2.5 liter SI automobile engine operates at wide open throttle on a four-stroke air standard Otto cycle at 3000 RPM. The engine has a compression ratio of 8.6:1, a mechanical efficiency of 86%, and the stroke to bore ratio is 1.025. Fuel is isooctane with air fuel ratio 15, a heating value of 44,300 kilojoules per kilogram, and the combustion efficiency is 100%. At the start of the compression stroke, conditions in the cylinder combustion chamber are 1000 kPa and 60 degrees Celsius. It can be assumed that there is 4% exhaust residue left over from the previous cycle. So this is the statement or the data given in this example. And the requirement is to do a complete thermodynamic analysis of this engine. Let me tell you very frankly, the statement of the example, it has a plenty of information available here. But in your practical life, you will not be having this much of information, and the boss or the senior or the superior will ask you to do the thermodynamic analysis of the system. And lot of data is missing or not available. So that will make your life miserable. This is what I teach or told to my students, that in practical life, you have to have so many assumptions, so many calculations, so many, you have to take account things which are not given in the statement. Now, coming to back towards the statement, let's analyze this statement. A four-cylinder. So we have an engine, the number of cylinders are 4. Okay. Now its volume is 2.5 liter. So total volume is 2.5 liter. It's an SI engine, spark ignition engine. Okay. At wide open throttle. So you know the condition, it's a wide open throttle and 4-stroke air standard Otto cycle. So you have a 4-cylinder engine with a volume of this, and SI engine with wide open throttle condition having a 4-stroke mechanism with N, the number of revolutions per minute, the RPMs are 3000. The engine has a compression ratio of 8.6. So RC is 8.6. Mechanical efficiency 86%. So you have the mechanical efficiency 86%, and we have a stroke to bore ratio. So its stroke and bore are not same. So it's a second condition. It's an undersquare engine in which bore is less as compared to your stroke. So there is with the ratio of 1.025. Fuel which we are using is isooctane, and the air fuel ratio, air fuel value is 15, which have a heating value QHV 44,300 kilojoules per kilogram, and a combustion efficiency 100%. So it's assumed that its combustion efficiency is 100%. At the start of the compression stroke, condition in the cylinder combustion chamber are, we have a pressure 1000 kPa and the temperature is 60 degrees Celsius. If the atmospheric condition is at 25 degrees Celsius, now at the start of the compression, we have plus 35. So it's 60 degrees Celsius. It can be assumed that there is 4% exhaust residue. So the exhaust residue at the end of the exhaust stroke inside the combustion chamber or the cylinder is 4% left over from the previous cycle. So now we have to do the thermodynamic analysis of this engine. What type of engine is this? How much it's developing a power, work, and all so many factors or which we have studied in chapter 2 and 3. Now, starting from the basic, first for us one cylinder, we will find the displacement volume. We know the volume of the engine is 2.5 liter. So we have a four cylinder. We divided it by 4. So the volume comes out to be 0.625 liter or this much of a meter cube. Now, we have found out the volume. We know the RC is given 8.6. From this equation, we can find out the clearance volume. So putting the values, we found out that the clearance volume is 0.0822 liter or 82.2 centimeter cube. So we have found out VD, we have found out VC. Now, using this equation, we are up till here, we are finding the basics. Now, VD we know for one cylinder, okay? Pi by 4 B square S is the basic formula of the volume of that cylinder. So putting the values, we get the bore value is 0.0919 meter or 9.19 centimeter. We know the ratio. Stroke is equal to 1.025 of bore. So the stroke value is 0.0942 meter or 9.42 centimeter. So now we have found out the displacement volume, we have found out the clearance volume, we have found out the bore, we have found out the stroke. So basic values we have found out. Now, remember PV diagram at state 1. State 1 at your piston is at 0.1 and it's the start of your compression stroke. Okay, so T1 60 degrees Celsius is 330 degree Kelvin. P1 is your 100 kPa given. So V1 is your volume at VDC. So volume at VDC is equal to your displacement volume plus the clearance volume. So adding both the displacement volume and the clearance volume, we get the volume at VDC or volume at 0.1. So that comes out to be 0.000707 meter cube. Now, at that point, we have found out the volume at 0.1. Now, mass of mixture at that point, 0.1. The mass of gas mixture in the cylinder can be calculated at state 1. The mass within the cylinder will then remain the same for the entire cycle. We taking as this assumption because we are using a standard Otto cycle. Okay. Mass of mixture is equal to P1 V1 over RT. P1 we know 100 kPa. V1 we have calculated. R is the universal gas constant and T1 is the temperature we have given. So mass of mixture is 0.000740 kilograms. So T1 is known, P1 is known, V1 is known, mass of mixture is known. Now, the compression stroke 1 to 2 is isentropic. Now, using the equations of pressure, temperature, and volume, P2 is equal to P1 RC raised to power K. Here we are taking K as 1.35. At point 1, the value of K is 1.4. At point 2, the value is 1.3. But we are taking the average of 1.4 and 1.3. So it is 1.35. Now, putting the value, we found out the pressure at P2 that comes out to be at P1, it was 100 kPa. At P2, because of the compression stroke, it is 1826 kilopascal. Now we have found out the pressure. Now at point 2, we'll find the temperature. T2 is equal to T1 RC K minus 1. Putting the values, we found T1 was 330 degree Kel, 333 Kelvin. Now we have 707 Kelvin or 434 degree Celsius. So P2 is found, T2 is found. Now we can find P2. T2, P2, we leave putting the values of these, and we found out the value of V2 at point 2. Remember, your piston is at TDC. When piston is at TDC, the volume is known as the clearance volume. So the same value which we have found for the clearance volume. Okay, same value. V2 and VC are the same. So same value. Now, this is the clearance volume of one cylinder, which agrees with the above. Another way of getting this value, we can find from this V2 is equal to V1 by RC, the same value we can found. Now, we have know the mass of the mixture. Now, let's find out the mass of the air, mass of the fuel, and mass of the exhaust residue, which is inside. So, mass of the gas mixture M in the cylinder is made up of mass of air, mass of fuel, and exhaust residual and exhaust. So mass of air, Ma, 15 is the air-fuel ratio of isooctane fuel which we are using. So 15 by 16 is that ratio. 0.96 because we have 4% exhaust residue. So 0.96 is remaining from the mass of the mixture. Okay, so the mass of the air in the mass of mixture is 0.000666 kilogram. Now same ways for mass of the fuel 1 by 16. We have 15 ratio 1 fuel. Now 1 ratio fuel. Okay, 1 by 16, 0.96 mass of mixture. So it comes out to be 0.000044 kilogram. Now mass of exhaust gases, as we know, it's 4% of the exhaust residue. So 0.04 into mass of mixture, we get 000030 kilogram. Adding all these three, it comes out to be your mass of mixture, which we have already calculated. Now, condition point at 2, we have found out the pressure, temperature, volume, and masses. Okay. Now at point 3, using the equation, because at point in process 2 to 3, we are getting heat addition in the cycle. So Q in is the mass of the fuel, heating value of the fuel, and the combustion efficiency of the fuel is equal to mass of mixture, constant volume, specific heat at constant volume, T3 minus T2. Okay, with now putting the value of MM, mass of fuel, heating value of the fuel, and the combustion efficiency is equal to mass of mixture into CV T3 minus 707 K. So T3 is equal to 3915 Kelvin or 362,642 degrees Celsius T max. So this is your T max. Okay, T3 is T max, and volume remains the same, and because it's a constant volume process, so V2 is equal to V3, which is the clearance volume, and that is this value. Now finding the pressure P3, putting the value in this equation at constant volume, we get the maximum pressure P3 10,111 kilopascal, which is P max. So we got the T max and P max. Okay. Now coming towards the point 4, which is the end of the power stroke. Okay. Now T4 is equal to T3 1 over RC K minus 1. So putting the value, we found out T4 1844 K or 1571 degrees Celsius. P4 P3 1 over RC K 10111 kilopascal 1 by 8.6. The pressure comes out to be 554 kilopascal. Now finding the volume V4. V4 is equal to V1 and that is volume at VDC. So same value is coming after putting this value in this equation. Okay. Now work produced in an isentropic power stroke for one cylinder during one cycle. Now W from process 3 to 4 M R T4 minus T3 divided by 1 minus K. Putting the value of mass of mixture into the universal gas constant T4 minus T3 K 1 minus 1.35. So the work done is 1.257 kilojoules. This is the work produced in an isentropic power stroke for one cylinder during one cycle. Now, work absorbed during isentropic compression for one cylinder during one cycle, that is work from one process 1 to 2, mR T2 minus T1 divided by 1 minus K. Putting the values, we get minus 0.227 kilojoules. So the work of intake stroke is cancelled by the work of the exhaust stroke. Remember this thing. Net indicated work for one cylinder during one cycle. So W net is equal to W1 to 2 plus W3 to 4. Adding both these, we get 1.030 kilojoules. So W net is 1.030 kilojoules. Now using these values in the equation, Q in is your mass of fuel, heating value of the fuel, and the combustion efficiency, we get 1.949 kilojoules. So indicated thermal efficiency, W net, work net, indicated work net, net indicated work divided by Q in. So we get 52.95 is the thermal efficiency of this engine. Okay. Another way of finding the thermal efficiency is 1 minus T1 divided by T2, or by using the compression ratio value, we found out the same 52.9%. So thermal efficiency of this engine is 52.9%. Now, finding the indicated mean effective pressure, IMP, we know the W net, so divided by V1 minus V2. So indicated mean effective pressure is 1649 kilopascal. So indicated power at 3000 RPM is obtained by using this equation. Indicated power is equal to the work multiplied by the number of revolutions per second divided by the number of cycles. Okay, so we are having a 4-cylinder, so it's a 2 revolutions per cycle. So putting value, the indicated power comes out to be 103 kilowatts or 138 horsepower. Now we have found out the indicated mean effective pressure, indicated power. Now finding the mean piston speed, the basic UP bar is equal to 2 into stroke into number of revolutions. So putting the values of the stroke and the number of revolutions per second into 2, we found out it is 9.42 meter per second and the range is 5 to 15 meters per second. Okay, so it is well in the range. Now the net brake work for one cylinder during one cycle. Net brake work is the mechanical efficiency into indicated work. 0.86 is the mechanical efficiency we know, and we have calculated the indicated work. That is 1.030 kilojoules. So the net brake work is 0.886 kilojoules. So brake power at 3000 RPM. The formula is like this: brake power, revolutions per second into number of cycles multiplied by brake work, net brake work into cylinders, 4 into cylinders. So that brake power comes out to be 88.6 kilowatt or 119 horsepower. Or we can find this another way by mechanical efficiency multiplied by indicated power. So it comes out to be same as 86.6, it is 88.6 kilowatts. Now, after finding the power work and power, now comes towards the torque. Torque is your brake power divided by 2 pi n. So brake power, we have calculated 88.6 divided by 2 pi radians per second. Then number of RPMs, revolutions per minute, converted into seconds. So torque of that engine is 0.282 kilonewtons meter or 282 newtons meter. Now, after finding the torque, let's find out the friction power lost during this whole process. So friction power is equal to indicated power minus brake power. So 103 minus 88.6, it comes out to be 14.4 kilowatts or 19.3 kilowatt is wasted in your friction power. Okay. Now, brake mean effective pressure. We have already found out the indicated mean effective pressure. Now will find the brake mean effective pressure. The mechanical efficiency into indicated mean effective pressure, we found out it is 1418 kilopascal. This allows another way of finding torque, which gives constant results. Torque is equal to brake mean effective pressure Vd divided by 4 pi. So putting the values, the answer is the same which we have calculated here, 282 Newton meter. Now, after finding this torque with another method, we comes to the brake specific power. So brake specific power is indicated, not indicated, the brake power divided by AP. AP is the area of the piston, and you are using 4 pistons, so multiply by 4 cylinders. So 88.6 kilowatt divided by pi by 4 into B square multiplied by 4. So comes out to be brake specific power is 0.334 kilowatts. Now output per displacement. Brake power divided by Vd, the volume of the engine. Okay. The brake power is 88.6 kilowatt and the volume of the complete engine, 4 cylinders, that is 2.5 liters, comes out to the output per displacement is 35.4 kilowatts per liter. Now finding the brake specific fuel consumption. Brake specific fuel consumption is mass flow rate of the fuel divided by the brake power. Mass flow rate of the fuel divided by the number of revolutions into the cycles per revolutions, 4 cylinder, and divided by brake power. So it comes out to be 180 grams per kilowatt hour. At the end, we find the volumetric efficiency for one cylinder using standard air density. Once for volumetric efficiency, as we know, is equal to mass of the air divided by the density of the air divided by the displacement volume for one cylinder, putting the value of mass of the air divided by density of the air at standard conditions and the displacement volume of one cylinder. So the volumetric efficiency is 90.2%. So this how we do the thermodynamic analysis of an engine. Let's see what we have calculated in this example. First, we have calculated the displacement. Okay. Then we have calculated the clearance volume. Then we have calculated the bore. Then we have calculated the stroke. Then at point 1, we have calculated the volume at P1, then the mass of the mixture, okay, at point 1 or state 1. Then we have calculated the pressure, the temperature, and the volume at point 2, okay. Then we have calculated the mass of the air, mass of the fuel, mass of the exhaust. Then at point 3, we have calculated the T3 max, V3, and P3. And at point 4, again, we have calculated T4, P4, V4. Okay. Then after finding all the basic parameters at 1, 2, 3, 4 points, the temperature value, the pressure value, the volume value, the mass values, then we find the work produced during the power stroke, then the work absorbed during the isentropic compression, that net indicated work. Then we find out the Q in, then we find out the internal thermal efficiency with two different methods. Then we found out the indicated mean effective pressure. Then we found out the indicated power. Then we found out the mean piston speed or average piston speed. Then we found out the net brake work. Then we found out the brake power with different methods. Then we found out the torque. Then we found out the friction loss, power lost. Then brake mean effective pressure. Then torque with another method. Then brake specific power. Then output per displacement. Then brake specific fuel consumption. Then we have found out the volumetric efficiency. So in total, we have calculated 35 different things to do the thermal analysis of this engine. So 35 different variables we have found, parameters we have found. So this is how the thermodynamic analysis is done. So this was the example 3-1 from your book. If somebody asks you to do the thermodynamic analysis of an system or of anything, you have to perform all these things, okay? More than 30 variables or factors you have to find, okay? Now at the end, as you know, I give assignment or the homework to my students. So this is your own study. If you want to study, you can study these a few other cycles which are knowledgeable to you. Okay, and you can go through with the example 3-2. Now again, consult book. This is the end of the lecture of this chapter 3. Okay, thank you very much. Do like my videos and subscribe my channel.